Okay, so the first this is a quantum design introduction. Okay, a quantum circuit design introduction. So it's just the very basics, and I have decided to do the whole thing with a standard Jupyter notebook, and I just guide you through the very basic steps of designing a quantum simulation. Okay, so the first thing we need is, and of course, if you have any questions, just let me know. Just let me know, and we can discuss. The first thing we need is the packages. Okay. As I said, later on you will get the code, so I'm just gonna be copy pasting from another file. And if you have any issues, so Qiskit is the IBM standard, and is basically what I use to design the quantum simulations. We have also the visualization mode, so that we can visualize the circuit, and then some standards for basic calculations. Okay. Once we do that and we load the packages, we can go and design our first circuit. Design first circuit with one qubit. Qubit is the unit of information. And the unit of information is coded into these qubits. For that, we just need to, we call it QC, quantum circuit, and then we say 1 qubit. Okay, so this is our first qubit, our first circuit, and it's basically there. It's called QC. Okay, so once we have this, we can design an initial state. This is basically designing some initial probabilities or position of the qubit, and defined initial state as the vector ket1. Okay. So this puts the qubit in a certain position, and once we have this, we can initialize the qubit. So we just apply this initial state to our QC qubit, initial state. And we do it like by doing so, we say QC dot initialize. So we are telling him to initialize the qubit. Then we are defining the initial state, which is the ket1 vector, and we say to which qubit we are assigning it. So the first qubit is always 0 in Python. Okay. So this just applies apply init to the zeros qubit, which is our QC vector. So this was successful, and after doing the initialization, we just draw the circuit. We do it, or I do it using the method MPI, because it's more beautiful. No, wait, MPL, sorry, MPL. I like it better than if you don't do MPL, you get a standard machine. I don't know what. I like it better. It's like more beautiful. Okay. So we have what you see here is a standard notation. We have our first qubit. It's called psi, and it has an initialization 0, 1, and on the first qubit. So the next thing we do is we tell Qiskit how to simulate our circuit. So there are several ways to simulate the circuit. There are several algorithms, and basically the algorithms deliver similar but not equal values when we do the simulations. So we can get the backend AER or AER, and we say we need the state vector simulator. Okay, so as I said, this backend is just a way to compute the tensorial products behind the information, so or behind the calculations. Insert cell below. We are going to perform our first calculation on this qubit, and for that we say, and our first calculation is just going to be to measure the state. Okay, so we say result get a state vector of the function, and then or of the qubit, and then we say just print the out state. Okay, so this is just going to display state vector. What am I doing wrong? Something wrong here. Wait one moment. Yeah, result. I need to name. Yeah. So here I need to create the first. I need to create the object, the Q object, and so this is to create the qubit object from the circuit for the simulator to run, and then we need to tell him what it means result. This is just doing the simulation on the and returning the result. Yeah, so this delivers our state, which is basically 0, 1. Okay, this is 0 here, real part, and 0 imaginary, and 1 real part and 0 imaginary. Okay, we can also measure this whole thing. And if we measure the qubit, we are just making it real. So measuring a qubit is just not reversible, as any other gate, as we will see later on, is reversible. But just this measure in the end is making the qubit is like projecting the qubit into a classic gate. It's called classic gate, and this is not reversible for in quantum terms. Okay, so we can also describe our probability states. QC, we call it result, same thing. And then we call it counts, so that it describes each state independently. And then we can plot a histogram of each of the probabilities of each one of these counts. Another mistake, result get counts. Yeah. So as you can see, this is not so surprising. There is 1.0 probability, so there is a 100% probability that the state is 0, 1. Okay, just as we could expect after defining the whole thing and doing nothing to it. So okay, any questions so far? Any of the steps that not clear? can continue. So we can design the second circuit, and by doing so we can create now a circuit that is in superposition. Okay, that is not 0 or 1, something in between. Initial state. Now we call it 1 divided by the square root of 2, and 1j divided by the square root of 2 again. And this is if you notice the squares or the sum of the squares of real and imaginary need to always to be 1, so that we have the unitary calculations, and later on we have a Hermitian Hamiltonian. This is necessary for quantum mechanics to work. So we define another quantum circuit. Okay, we can initialize it again with the initial state, which is now 1 divided by the square root of 2, comma, j divided, so the imaginary part, and we tell him this is the zeros qubit, this is the first qubit. Okay, so we put together the object, the circuit, and we tell him to run and execute the state vector calculation by doing this, and then we say print state. So basically the same logic as before, and now we get basically the state vector as it is described there. And if we now print the state vector probabilities, then we get 0.5, 0.5. So results equals as sim dot run key object dot result get counts, and then just plot a histogram, just basically as before with results. I always make mistakes typing. So basically you see we get 0.5, 0.5. This is what we would expect, being the state vector 1 divided by the square root of 2. And there is certainly a 0.5 50% probability of 0 and 50% probability of 1, which means that this vector is entangled, and it is neither black nor white. Yeah. So this is about the entangled vector, and now we get some intuition onto the graphic representation, or how qubits are graphically represented. This is made with a Bloch sphere. Okay, I have here a little image so that you get the, yes? Yeah, no problem. Yeah. We can measure after the out state, and we will get 0.5 and 0.5. So this is basically the probabilities. Once you decide, then you will get 0.5, 0.5, and basically the sum of these two blue columns should be 1. Okay, so Yeah, and then it is not reversible. Then you cannot go back. Then you have decided, and you have, yeah, yeah, you have flipped the coin, and then that's it. Yes. Yeah, you have one qubit that can either be in position 0 and or position 1. Yeah, one qubit which is entangled. Yeah. Yeah, sorry, it's in superposition. Yeah, yeah. It's yeah, sorry, it's in superposition. Entanglement is with 2. Yeah, yeah, correct. Yeah. It's in superposition. Correct. Yeah. Okay. So you have here the mathematical expression if you describe a qubit into in the space. Okay. And you can describe this into the so-called Bloch sphere. And for that, so this is basically something like this, right? This is just if we have the coordinates pi divided by 2, 0 and 1, which is theta, phi, and the radius. Okay, so just as in the formula, then you get something like this. Okay, so you see always a 0 is pointing up, the 1 is pointing down, and then you get the vector pointing into the x-axis. Okay. And this is basically an intuitive way to describe it was first a little bit difficult for me. I'm not a physics. So I didn't know much about this some time ago. So at first was difficult for me to understand this graphical description, because the 1 is actually should be not looking down, but only looking on the plane. So just on pi divided by 2 degrees to 0. But yeah, at some point I understood that this is just a graphical way to describe it. So there are certain gates, okay, that are interesting for our circuit. Quantum gates are interesting for our matter today. So the first one is the so-called Pauli gate or Pauli gates. Okay, there are several. And basically the intuition is that you rotate this vector around one of the axes x, y, or z. Okay. So if we describe the let's say the x gate, okay, I'm just gonna make one example. X Pauli gate. Basically, you would be revolving. You would be turning this vector around the x gate. Okay, so basically what we do is we multiply with a certain matrix. The mathematics behind it is like that, basically if we have a quantum circuit and we apply if we have a quantum circuit and we apply the Pauli gate x on it, or if we have one qubit better, and we apply the quantum qubit, the quantum gate x gate Pauli or x Pauli gate, we now see what happens. Quantum circuit. It's a little bit difficult to talk and type, but so you do this like this. So you apply the x gate and to the first qubit or to the 0th qubit, and by doing so you just say quantum circuit qc.x, okay, and then you say qcit draw in MPL, and then you get just that, okay, you get a little and if we want to visualize what this does, okay, you remember QC is it was initialized as something like 0, 1, okay. If we turn 0, 1 around x, then we are going to have the vector looking down. So if we want to see what happens by doing this, we just need to apply the state vector simulator and the Q object and then the state, and then we see that the qubit that was initially looking up is now looking down, because it just rotated around the x axis, okay? Yeah. Heading above. So another important gate is called the Hadamard gate, which creates a superposition of 0 and 1. This can be thought of as a rotation around the Bloch vector 1, 0, 1. Okay, so is basically the line between the x and the z axis. Okay, or this transform the state of the qubit between x and z axis. Mathematically speaking, you get this. Okay. All these matrices are unitary, and there is a little demo here you can play later on if you want to understand these gates. So if you run the gate demo, then you can, okay, you have one qubit looking up in the beginning, and then you say, okay, I'm going to turn it with an X Pauli gate, and then see what happens. Now if I click on the X, it should look down. Okay, so it looks down. If I click on the X again, looks down again. Okay, so if I rotate around the y-axis, it should look down again. It just turn around, not x-axis but around the y-axis. If I rotate this vector around the z-axis, nothing happens. And if I rotate it around the line between the x and the z-axis 45 degrees, then turns as expected. Okay, so you can just play, and it's kind of fun, and then you can go back and reset it. Okay, so this is a very intuitive way just to try to understand what this whole thing makes. And also, any questions so far about these two gates, or is it clear? It's okay. Cool. Well, then if we go and just increase the difficulty a little bit, just a tiny bit. Now we can describe the most general gate. It's called the U gate. Okay, there are like I don't know, 50 gates or something, but interestingly enough, this U gate does everything. Okay, so it's just a generic way to rotate a qubit. So with this U gate, you can achieve anything, any state or any rotation the rotations are going to be important later. This is going to be all about probabilities, so these rotations are going to be turning into probabilities. So it's kind of interesting. The intuitive behind it is this math, okay? And with the U gate, we can change all these theta, phi, and lambda parameters, and then we can just achieve any rotation that we want. Okay. These are single gates, okay, single qubit gates. Let me maybe here better single qubit quantum gates. So these are, I think, the most intuitive or important. You have also the Y gate, Pauli, or you have, I don't know, you have the Z, you have the H, I don't know. There are some of it, some of them. I will send you later on an intuitive guide where you can find more if you are interested. So now we go and we describe multiple qubit quantum gates. Okay, and the first one that maybe it's kind of interesting is the C-node gate. The C-node gate is a conditional gate, okay, that performs an X gate on the second qubit, on the target, if the state of the first qubit or control qubit is 1. Okay, so I am going to write it. The first time you see this is kind of okay, what the fuck? I don't understand it, but it's kind of difficult. It's kind of easy. It's just like a if gate. Okay, so in the classical world, conditional gate that performs. If you read it slowly, it's easy. Okay, an X Pauli gate on the target qubit. If, and this if is important, the state of the first or control qubit is ket 1. So this gate goes like this. It just looks at two qubits at the same time, and it looks at the control. Looks, are you 1? Are you looking down? And if you are looking down, then I perform an X Pauli gate on the second one. Okay. So if you describe, now let's see how this looks like. If you describe a quantum circuit with 2 qubits, and then you say I am going to apply a CX gate on 0, 1. Okay, 0 is the control and 1 is the target. Okay, so Q0 is the control and Q1 is the target. And then you say QC.draw in MPL, and let's see what happens. So basically what this is doing, this is rotating the Q1, okay, where you see a plus, okay, this target, that's why it's a plus. And if after looking at Q0, Q0 is in the state of 1 ket. Okay, does it make sense? This is also called the CX gate, C0 or CX. C. Well, this is one of the if you use the CX enough times combined with Hadamard, and with U rotation and with Pauli gates. I am not an expert, but I believe I can build or you can build basic circuits. I don't know if any circuit, but because for instance you can have also the Toffoli, which is the next one, the CCX, and you can build a Toffoli based on this basic. It's like can you build in a classic program any program with just if then else routines? Well, maybe you can, but it's very difficult. So that's why you. Yes, yes, correct. Yeah. Yes. Mm-hmm. So sorry. Insert cell below, and so the next one is the CCX, or it's also called Toffoli gate. This is a 3-bit or a 3-qubit gate with 2 controls and 1 target. Okay, and here is the same logic. It performs an X Pauli rotation only if both controls are in the state of 1-ket. So it looks at 2 controls, and if both are in 1, then it's cool, and it rotates the target. So we call A with 0, B is the 1, and T is the 2, and then we perform CCX on the quantum circuit. Basically, there's a convention here. You say A, B, and T. Okay. So both controls are A, B, and the target is the last one. And then you say QC draw MPL, and then you click Shift Enter, and that's the way it looks like. Okay. So any questions? So I don't know what's your level, so this is just really basic stuff, but I guess necessary if you have never seen anything like this. So now, what parts do we have in a quantum circuit? This is also, for me, it was not intuitive, but with this picture, maybe it becomes intuitive to you. I don't know if you can see the figure. So you start with your qubits, okay? Q0, Q1, Q2. Then you create your initial or your initialization and reset. Basically, you are giving some energy to each qubit. Then to initialize the position, to put them in a certain angle, or if you want to leave them just in 0, looking up, whatever. Okay, so the standard is just leaving them in 0. Then you place your quantum gates following a certain logic, and then you measure. Okay, when you measure, you're projecting on certain axes. So as you see, I put here a projection on the axis Z, CRZ, and CRX. So you're projecting the information into an axis, and then basically you can put, after the measurement, you can put classically controlled quantum gates. Okay. Anything that happens after the measurement is not reversible. So this is basically the elements of the quantum circuit. And now it gets interesting, but before I can ask, is everything, could you follow so far, or do you have any questions? Mm-hmm. Yeah. Yeah. Mm-hmm. Yeah. Mm-hmm. This is at least the way I understand it. We have physics in the room. Rosa, I think Laia is also expert here. So this is the way I understand it. So when I have a circuit, I repeat the measurements maybe 8,000 times. This is the maximum that the IBM cloud machine allows, and then I get 8,000 measurements, and then I have a Gauss curve giving me the measurements and some statistical error. This is the way I do it so far, but I'm just I don't know. I don't understand quantum mechanics in very depth. Okay. Mm-hmm. Mm-hmm. Correct. Yeah. Yeah. I think so. Mm. Okay. Any more questions or? Okay. Well, thank you very much. And then we can now advance. What is the meaning or what is the geometric intuition between rotations and probabilities? Okay. So if we look at the let's say geometry of the sphere, we can easily see this. Okay, the theta is 2 times the arctangent of the tangent of theta divided by 2, and this is 2 times the arctangent of the square root of the square of the sinus of theta divided by 2 divided by the cosinus of theta divided by 2 square. And if we follow the intuition behind this equation on the line 25, we will see that this is just the probability that it is 1 divided by, or the square, 2 times the arctangent of the square root. That is the probability of get 1 divided by the probability of get 0. So following this intuition, we can actually start designing a quantum circuit, okay, in a serious manner. Okay, so I am going to start following this intuition. I will apply this this logic to the design of a 3-qubit quantum circuit, and I will try to do it just step by step. Okay, qubit 1 is connected to qubit 0. So, and qubit 2 is connected to qubit 0. So we have sort of a network of 3 qubits, and the qubit 1 and the qubit 2 are connected to the qubit 0 with known probabilities P1 and P0. Okay, and what we want is to state the final state of this system, of this small network of 3 qubits, with help of a quantum circuit. Well, I will go step by step. So the first thing is well, we know this, the packages. Then we need a quantum register. Okay. We need a quantum circuit with 4 qubits. The reason why we need 4 and not 3 is because we need an additional qubit to perform the CCX and this Toffoli gates and C0 gates and CX gates to support our rotations. In the case that we have, in this case, we have 1 qubit, which is a qubit 0 that has two qubits, let's say, reporting to it. We need 1 additional qubit. If we would have, let's say, 1 qubit receiving 3 arrows in it, we would need 2 additional qubits, and so on. So these additional qubits are called ANSIA qubits. Then we want a classical register also to perform the measurements. Okay. And we also need 4 to measure the states in the end. And the circuit is going to be a quantum circuit that combines the quantum register and the classical register. Okay. Then we are going to give the qubit its rotation. So the quantum the qubit 0 is going to have 4 states. Okay, 4 possible states. 0, 0. Wait. 0, 0 in the initial manner, so 0, 1, 1, 0, and 1, 1. And the other 2, as they don't have any parent, are only going to be 1 or 0. Okay, so we just need so this is for qubits with two sons, or with two parents, sorry, and qubits without parent. And so we describe some rotations that are going to fit just some random numbers, theta, q0, 0, 0, and so on, 1, 0, I don't know. (1.14), and this is for the qubit 0, and then we get also for the qubit 2 0.85, I don't know, and for the qubit 3, I'm going to call it 3. That will be the ancilla node. Will be the 1. Qubit 3 equals 1.09. So the first thing we do is we reset our qubits. Okay, so this is basically the first part in our universal diagram. Okay, we have an initialization and reset. After that, we perform some rotations. Let me copy them and just go step by step through them, or just walk you through the rotations step by step. Of course, I prepared this before, and then we measure. Okay, so this is just the three parts of our reset and initialization, rotations, and measurement. Okay. So, and here the important part is that qubits without parents. Okay, so as you see here, the quantum register number 2 and number 3 experience an initial rotation. This U3 is the classical universal rotation. Experience an initial rotation and nothing more. No rotation directly. Only experience these single rotations. Okay. And however, this qubit number 0, okay, which has two parents, experiences several times this rotation. So you see here theta q011 and then minus theta q011. And the reason for this is that we are going to apply systematically, and you see this for all the possible combinations, so 1 1 and then 0 0 and then 1 0 and so on. The reason why we do this is because we are going to apply to these qubits with parents, we are going to apply a single rotation of in one direction, and then we are going to apply CCX meaning that if the initial rotation has turned our Q0 qubit and has put it into a state of 1, then this CCX after that is going to apply an X Pauli gate on it, and is going to put it again into 0. Okay, if the initial rotation didn't put our Q0 qubit into state that is not sorry, if the qubit, if the ancilla qubit is not put into 1, then the Toffoli gate is not applying. If it's put into 1, then it rotates again another theta q011 in the opposite direction, so that nothing happens. Okay, so this is basically the trick. It's going forward, checking if the ancilla qubit is put into 1, and if so, turning it back, rotating it to its original position. Okay, by doing so, we create the systematic, this whole circuit, and in the end we measure 0, 2, and 3. Basically we can simulate the circuit and get the job result. Okay, getting the counts or the state probabilities, and describing our circuit. So we can print the counts. What happens here? Quantum circuit needs to be big. What happens? Quantum register, not quantum circuit. QK is not defined. Oh, yeah. Sorry, I forgot some. So as you see, we get the states of the circuit. We get the state of the circuit. We can, of course, paint this in a histogram. And you can see that the states, it's kind of tricky, because the last number in this state is given for Q0, the second is given for Q1, so the ancilla, the third, so if you need to read it from right to left, okay? So the first number is for Q0, for Q1 is 0 here, for Q2 and Q3 and so on. So the square of 0.082, it's going to be then 0.049, which is basically this. So if you add up all this blue columns, you will get 1. Okay. You can print the circuit, of course, as we have done before, a little bit in a pretty way. And with basically with the circuit printed, it is easier to explain what we have done. Okay, so let me put it a little bit bigger. Maybe it's easier to see. You can see here the first thing we do with this black initialization is to initialize all the qubits in zeros. Then we get an initial rotation U3 on Q2 and Q3, which is basically this rotation. So this is the initialization, okay? Then we get the initial rotations here. Here, the two initial rotations, and then we start applying either Toffoli or CX in a systematic manner. Here, with a rotation a little bit bigger. No, it doesn't let me. I don't know if you can read it, but here I rotate in the Q0, I rotate it 0.411, and then I perform a CX gate, and if after the rotation the qubit, the target qubit Q0 is in 1, then please apply a rotation around X and place it again to 0. If not, turn it back to where it was by rotating it again back to its position. Okay. So, and my time, I guess it's over. I have 3 minutes. I scheduled for 1 hour. Do you have any questions? Yeah. So basically, this is simulating a Bayesian network of 3 elements, the element 2 and 3 with conditional probability to the element 0. So by doing so, or by describing this Bayesian network with a quantum circuit, we are able to describe our decision network. If you, it's a Bayesian, I say Bayesian, but it's more a decision network, okay? Where we can, and because many physical or many industrial processes can be described by decision networks, with this method we can describe industrial processes or decision processes in real life, in economics, or by using quantum computing, or by using quantum simulations. This is basically the idea that I wanted to talk to you about last week, Laia. A little bit expanded. I am going to give you some references if you, but this with this methodology, basically what we can do is we can simulate anything that is related to a decision. Okay, so anything that can be simulated through a decision or Bayesian network can be potentially be described with a quantum simulation process. And by doing so, we get superior performance computation-wise than what we get with just classical computation. This goes faster, and I don't know, but basically any process that involves a decision, okay, and where you know the conditional probabilities, because the conditional probabilities are these rotations. Yeah. Fortunately, in just 1 hour, I didn't have time to go into depth, but this is what I wanted to explain with these arrows. Yeah. Okay, so if you have interest, here under this link, you can find some papers. Not all of them are about this, but some of them are about this, where some strategical organizational design configuration. So people making decisions, basically, Laia. So if you report to your boss and the probability that you succeed. Okay, let me give you a very simple example. Okay, if you are in a company and you have a boss, okay, the probability for the boss to be successful depends on the quality of my work. So if you can measure the probability of the boss having success based on some KPIs, performance indicators, and you can measure the probability of me having success with my performance indicators, then we can simulate the system, let's say the managerial system, with quantum simulations. And then we can say, okay, the probability that the boss is successful is this and that, or the probability that the boss is successful by 90% can only happen if his worker or her worker is 99% accurate. Well, it's faster and it's more, let's say, computational wise, is more efficient. It grows for just some few qubits. It's similar, but if you grow this for, let's say, 20 elements, then the Bayesian just collapse at some point. Yeah. No, well, each qubit can be anything. It can be, let's say, it can be a worker. It can be one sensor. Okay, let's say yes, yeah, yes. Mm-hmm. Mm-hmm. Yeah, yeah. Yeah, so basically what you need to do is you first need to calculate the conditional probabilities, okay? So this is just Bayes theorem, okay? So if you have, let's say, a time series for each element, then you just apply Bayes theorem to however you want to model your, let's say, your digital twin, okay? So there is some expertise needed, and you need some know-how about the process. And then you need to say, okay, I think the network should look like this, and the conditional probabilities are like this. And you can calculate that based on Bayes theorem or some, let's say, classic statistics. And once you have your probabilities, let's say your P1 and P0, okay, you just go to this formula on line 38 and calculate your theta, okay, your angles. And with the angles, you just follow the logic step by step and calculate the circuit and the state probabilities. In the end, it is always necessary to check if the classical Bayesian network delivers the same result as the quantum circuit. If it is not the case, then something is wrong. Yeah, the radius is always 1. Yeah, yeah, yeah. So the radius is always 1. This is just a convention. And theta is the only thing important because we are projecting on the z axis. This is also a convention. Yeah. So we could be projecting on any other axis, but I don't know anywhere where people do something different. I at least. Yeah, yeah. So yeah, 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 yeah. So I don't have a lot of experience. I'm just doing this since, I don't know, maybe 8 months now. I before I didn't know anything about this. So and as I said, I'm not a physics. I'm just a poor engineer. So I don't understand many things about quantum computing, but I guess it's a useful way to crumble the cookie in certain nice ways and get some nice applications. Yeah. So yeah. Yeah. Okay. Well then. Anyway, any more questions, or was it okay for you this way? Oh. Yeah. So so if you have any questions, just let me know. I see there is Tino, somebody called Tino. Ah, okay. So I don't have Tino's email, so I will forward you the PDF and the link for the video. Okay, that I just made, and I will send you the links. Please forward it. Okay, is that okay? Mm-hmm. Yeah, great. Thank you. Perfect. Cool. All right, let me just copy it. Stay on the side. I'm gonna copy it to the. I will copy it into the thing. Okay. Great. Cool. Well then, thank you very much for your time, and have a nice weekend. Bye bye. Bye bye.